Hello, so in the next series of videos and the lectures and labs this week, we are going to be looking at something called Gaussian elimination. And the four things that we're going to be looking at are, I've written them down on the screen. So the first thing is, what is Gaussian elimination? Why is it useful? Why do we care about Gaussian elimination? The second thing we're going to look at is something called naive Gaussian elimination. So we're going to look at forward elimination and back substitution within that. That's really to get the idea of what Gaussian elimination is doing. We're then going to ask the question, okay, how can we make things a little bit more efficient? How can we solve this Gaussian elimination method a little bit more efficiently? So we'll look at a couple of different methods to do that, and they're going to be partial pivoting and LU decomposition. So hopefully, by the end of the labs and lectures this week, you should be comfortable at being able to answer these 4 points, and you should be comfortable with working with these 4 ideas. Let's start off first of all though, by using the motivation of why is Gaussian elimination useful? So let's suppose we have a factory which consists of 2 departments, so Department A and Department B. And the issue is that I'm an external person coming in and I want to figure out how many people this factory has got working in each department, so Department A and Department B. So I don't know that directly, but I do have some information which should enable me to be able to work that out. So let's suppose, for example, that I know the hourly pay in each department. So let's suppose that the hourly pay in Department A is £13 per hour, and the hourly pay in Department B is £15 per hour. Perhaps they're doing slightly more tricky work, which means they deserve a higher pay rate. And also, I know the total amount of wages that the company pays every single hour. So let's suppose that's £228 every single hour. Now, using this bit of information, so the hourly pay, I should be able to work out an equation which should get me closer to being able to solve how many people are working in each department. So namely, if there's £13 per hour being paid to every single worker in Department A and £15 per hour being paid to every single worker in Department B, and I know that should add up to 228, I can say that 13 times the number of workers in Department A plus 15 times the number of workers in Department B should add up to 228. Now I just want you to pause the video and think for a second. Is this enough? Can I work out directly how many workers there are working in Department A and Department B? So hopefully you've had an opportunity to pause the video and have a think about that. And hopefully you've decided that the answer to that question is no. There's still an infinite number of values for A and B, an infinite pairing of values for A and B, such that this equation will hold. So I need some more information. Well, alright, let's suppose that I have some extra information such as the number of hours that each worker works in each department per week, okay? So let's suppose that the number of workers in Department A, they work 60 hours per week. So they work 60 hours per week each. And Department B, they're really overworked, they work 200 hours per week, okay? And I know that the total number of hours across all the workers is 2,360 hours every single week. Now using this, I should be able to form a similar equation to how I formed with the hourly pay, which would be 60 times the number of workers in Department A plus 200 plus the number of workers in Department B. That should add up to the total number of hours every single week, which is 2,360. Now you notice here that I've formed a system of 2 equations. The idea is that A and B should remain the same. A and B are my unknowns. That's what I want to find. It's the number of workers in Department A, the number of workers in Department B. And I've formed a system of equations using some information which I already know. So I would call this a system of equations. The idea is I know that A and B should be the same in both equations, and I should be able to work out what those values of A and B should be. Now in general, there will be a lot more unknowns, okay? So you could be looking, for example, 7 or 8 unknowns. So my question is to you, and you might want to pause the video now, how many equations would I need in order to solve that many unknowns? So if I had n unknowns, how many equations would I need? So pause the video and have a think about that now. So hopefully you've had a think about that, and hopefully you've realised that the number of unknowns means that you need that many equations. So for example, in this case, I had 2 unknowns, and we said that after the first equation that I formed, there was not enough information here in order to say with absolute confidence what the value of A and B is. Of course you might guess it, and you might guess it right, but you wouldn't know with confidence whether that would be right. In order to say with confidence, you needed another equation, because there's 2 unknowns, therefore you needed 2 equations. If you had 7 unknowns, you would need 7 equations. 100 unknowns, you need 100 equations. So in general, n unknowns means that you need a minimum of n equations in order to solve that. Now, fairly obviously, I've given you a fairly trivial example here because I wanted you to get the idea and the motivation behind solving equations with unknowns. But you should be able to solve equations like this. Like, you've probably been looking at simultaneous equations since the age of maybe 13 or 14. You may have a multitude of different methods in order to solve this. But what I want to do is say, well, okay, if we have more than 3 or 5 or 7 or 9, however many unknowns that we've got, can I form a system, can I form a method in order to be able to solve that many unknowns? Because solving 2 equations is pretty straightforward, but solving more than 2 equations, it becomes a little bit more tricky. So I want to come up with a method to be able to solve that. And this is where Gaussian elimination comes in.